In the world of computer science, you often hear about famous data structures like arrays, stacks, and binary search trees. But lurking quietly behind the scenes is one of the most elegant, efficient, and surprisingly powerful tools, the Fenwick tree, also known as the binary index tree. The Fenwick tree solves a very common and important problem: how to update numbers in a list and get fast answers to range-based questions. These operations appear in almost every performance-critical software system, from finance analytics and gaming engines to time series dashboards. What makes the Fenwick tree special is its perfect balance between simplicity and speed, giving you near-instant answers to cumulative queries. Despite this, it is far less popular or well-known than other data structures that do the same job, like segment trees. Imagine you have a very long list of numbers, like daily sales totals or player scores. Now imagine needing to answer questions like, what is the total of the first 1,000 items? Or what is the sum from item 300 to item 700? If you walk through the entire list each time you needed a sum, it would be very slow, especially if the list updates frequently. You need a data structure that can quickly update individual values and quickly return totals over a range. A regular array is good for fast reads, but slow for range totals. A prefix sum array is good for range totals, but slow for updates. A segment tree can do both extremely fast, but it's complicated and memory heavy. This is exactly where the Fenwick tree shines. A Fenwick tree stores partial information about your list in a smart, compressed way. This allows you to update an item very quickly, compute running totals very quickly, and use very little extra memory. The trick is that the Fenwick tree keeps track of selected, cleverly chosen chunks of the original data. Each position in the structure represents the total of a small segment of the list. These segments are arranged so that when you ask for a cumulative total, the data structure can jump through memory in large steps. Instead of recalculating giant sums from scratch, it retrieves information from these segments, combines them, and returns the answer almost instantly. The beauty of the Fenwick tree is that it divides the array into overlapping chunks, each representing a portion of the data. For example, one chunk might store the total of the last two numbers, another the last four, and another the last eight. When you need a running total, the structure jumps through these chunks like stepping stones, each step covering a larger piece of the list. This chunk stepping is what makes the Fenwick tree so efficient. Despite solving such a fundamental problem, the Fenwick tree is often overshadowed by the more general segment tree. However, for fast updates and running totals, the Fenwick tree is often simpler, faster, and much easier to implement. Its name, Fenwick tree or binary index tree, doesn't immediately tell beginners what it does, leading many to overlook it. Programmers often use brute force loops or caching tricks without knowing there's a clean and principled solution. Fenwick tree code for both updating and querying is usually only a few lines, making its power deceptively simple. It quietly powers online game ranking systems, financial dashboards, and search engines. Anywhere you have numbers that change and need to compute running totals, a Fenwick tree is often the smartest tool. Mastering the Fenwick tree gives you a clean and elegant way to handle dynamic datasets and a powerful alternative to heavier data structures. Most importantly, it teaches you how far clever organization can go in speeding up your programs. The Fenwick tree is one of the most underrated data structures because it's simple, fast, lightweight, and perfect for a class of problems that appear everywhere. If you're building anything involving frequently changing values and fast cumulative queries, the Fenwick tree is not just useful, it's essential.